Welcome to Spring LIB.
So the situation before collision and after collision are drawn in the picture, where this is the rod or the bar, and this black dot is the metal ball that hits the bar. Now, to solve this problem, we see that we first consider the counterclockwise rotation as a positive direction. Now, if we want to calculate the moment of inertia of the bar, we call it I. This will be 1/3 m2 L squared, where m2 is the mass of the bar and L is the um, length from the pivot point to the end of the bar. So that's why it's 1/3. Now, we'll be applying conservation of angular momentum here. So if we do so, we see that before collision, the only angular momentum was due to this black ball, this black dot or the metal ball that's hitting the bar. So for that, before collision, the total momentum will be m1 times v naught times d, where d is the distance from the pivot point to the point where the ball hits the bar. So that's before collision. And after collision, there will be angular momentum due to the ball going away. So it's a negative sign because it's going in the opposite direction, but it will be m1 times v, where v is the velocity it after the collision, and d is the distance again from the point of hitting to the pivot point, plus since the bar starts swinging, so it will have the so the angular momentum will be I times omega, where I is 1/3 m2 L squared times omega. So this is after and this is before, and due to the conservation, they should be equal to each other. So if we do so, and if we then solve for omega here, omega is the angular speed of the bar. So we're given m1, we're given the velocity before collision, velocity after collision. We're given the point where the metal ball hits, and then we're given the weight of the metal ball. So to get the mass, we just divide the weight by gravitational acceleration, and L is 2 meters. So using L is the total length of the bar. So if we put all the numbers, we see omega is 5.88 radians per second. Now, to explain why the angular momentum is conserved, we see that there is no unbalanced torque about the pivot point, and that's the reason why the angular momentum is conserved. And but we see that the pivot point exerts an unbalanced horizontal force on the system, and that's why the linear momentum is not conserved. So this is the reason for linear momentum not being conserved. Thank you.